Okay. Uh, Today I'll talk something about the renormalization group. Recently, I'm reading some papers about the adjective gravity and its dual matrix ensemble, and I found some very primary, not primary, ordinary paper. And in this paper, the author try to calculate the high temperature expansion for the double scaled SYK model. Then he argues that if we can take a log for the z beta, then he found that the first it can use the asymptotic expansion to recover the first zeros or the first singularity of the log z. But these things are quite trivial, so uh, I want so I explored that if it is possible to get to obtain the second singularity or second zeros or other end zeros of the z beta, and I found that it is quite sensitive to the numeric precise. Okay, so I found that all of these things are quite meaningless because you can just to use an approximation to 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 calculate the z beta, and just then you can use other very simple method to calculate its zeros. Okay, that's great. Then let's move on. We'll talk about the renormalization group. The renormalizing. This is because recently I'm sorry. I teach a class. I teach a course of QFT to some remote student. So to a remote student. So I just record it for me, and if it can be a little helpful to others, I think it's quite it is the biggest player to study physics here. Okay, then let's study on. Then why we want to understand the renormalization group, it is how to say, it is a thing sort of style. It's a sort of style to understand QFT as an effective theory, and it is an important tool. It is an important tool to sorry. It is yes, it's an important tool to understand the phase transition. It is important to understand the non-perturbative effects in the field theory. Okay, the orange idea you can see is from the two of the papers of Wilson. But here we found that the discussion in the book quantum phase transition can give us quite insights to this topic. So I just follow the content in this book. So at first we need to see we take the classical phase transition as an example. What does it mean when we say classical phase transition? Which means that in the Hamiltonian, you just regard everything is the C number. Okay, for example, when we consider the n-component spins, classically we just regard it as a vector with n components. Okay, but quantumly it should be some operator. For example, for spin in 3 dimension, classically it is a vector. It is a unit vector. It is continuous, but for the quantum case, it is not a vector. It is a vector of the 3-point matrix. So this is difference. Or you can just think that for the classical phase transition, the H is not a matrix, or it is a diagonal matrix. So it's quite direct to calculate the path transform, the partition function. You just need to sum over all configurations. Yes, you do not need to calculate this exponent because H is just a scalar number. it is a scalar number for any configuration. But for quantum case H, it should be a matrix with quite large dimensions, and then it is quite hard to calculate the exponent of a large dimensional matrix. Okay, this is a key point we want to comment. For n equal to 1, then we know that it is n equal to 1. Okay, component. What is n equal to 1? Anyway, this is as a model. It have two freedom. One freedom up and one freedom is down, and then you can just choose some overall configurations. For the 1D and the 2D case, you can just go to the analytical result of the partition function, and it is quite beautiful, quite nice to study its phase transition and other things. But for general case, it's quite hard to grade. And we know that any observables O can be calculated from the partition function. You can calculate it by partial sum some parameter in H, for example, the beta and anything. You can get the freedom and the free energy and anything. Okay, and the ensemble average is defined like this. Okay, here we can to do some very rough approximation. The first thing is we can do is the mean field. The mean field, maybe it can be very rough, but it can be very rough, not so good, but it gives some our insight to understand the physics. Suppose that you are a spin at the site I, then you try to then in the Hamiltonian, you know that your neighborhood the sigma j can have some effect on you. Okay, if you just use a mean field to represent it, it means that for every site I, it feels the same effect. It feels the same effect for its neighborhoods. Then we just denoted it is a constant. It's a constant parameter, and this parameter we need to. This is the parameter we need to optimize. Or need to optimize. That is because what we study, the system we studied has a very large number of particles as the number of the spins. It is quite large. When n is quite large, the system tend to choose the state with the minimal free energy. Okay, so we need to minimize the free energy. Okay, that's great. Then we can calculate it. Okay, we just replace its neighborhood just with a mean field parameter. Then we need to solve the self-consistent equation, which means that we just use this one as a mean field Hamiltonian and calculate the spins average. Then we get this equation. Then we solve the equation. You can see that for k is quite is small, there is only one solution, n equal to 0, which means there is no magnetism. Okay, no magnetism. The spins are quite random. The spins are quite random. Okay, but when you vary k to a large k, you can find that there is a sweet solution. You need to compare the free energy of the sweet solution, and finally you will find that these two solutions have the minimal free energy. So, but you need to choose one among them. The original model has the Z2 asymmetry, which means you make sigma I to minus sigma I. Then the Hamiltonian is invariant under such transformation, but for the large k, you need to choose one of the two states as the not as a ground state. That's because for the non-zero temperature, the true state we see is a state with a minimal average, or not the minimal Hamiltonian. Okay. Okay, and we want to choose one of it, so you can draw the phase transition. Actually, what we do is just a special type of the variational methods. The variational methods, which means that it based on this inequality, which means that we can choose a simple mean field Hamiltonian, then use this Hamiltonian to calculate this thing, and it is a bound of the exact free energy. It is served as approximation. Okay, that's great. And then we just use a single site Hamiltonian to calculate. You can find the explicit expression for the. Okay, it is approximation of the free energy. Then you can plot it with with n0, and you can find that for k is large than a critical kc, you could see that there is two position has the same minimal free energy. Then from this figure, you can see that the orange theory has Z2 symmetry, but finally you need to choose one state of the 2 point. So it is an example of the spontaneous symmetry breaking. Actually, there are two types of symmetry breaking. One is the spontaneous symmetry breaking, and another is the dynamical symmetry breaking. I think the difference between them is that the spontaneous symmetry breaking is that we just take the field to be a constant, then we just plot the free energy, then we can see that it is a transition. But for the dynamic symmetry breaking, we need to consider the loop correction. The loop correction, one loop and three loop and other thing to give a correct diagram. Then we can see the phase transition. This is dynamic symmetry breaking. Okay, this is my personally understanding of this topic. Then we consider the non-dose theory. You can see that you can regard all of this discussion as a kind of approximation. The mean field theory is nothing but to use one parameter to replace the large freedom. The large freedom is the spin itself. Freedom is spin up and spin down. You have many freedoms, but then in the mean field theory, just use one parameter to approximate to describe it. But you can do the same. You can do better. That is because you can do some, how to say, the coarse grade average. You can describe the system more. You can describe the system more detailed. Yes, this is what we want to do. So, but we don't want to describe every spin in a system. It is quite hard. So we just take some, how to say, some neighborhood of a place X, and we just sum over all spin around it in this neighborhood. Okay, in this region, then we denote it is we define it as the value of a field on X. Okay, in the original system, as X is discrete, but finally we will make it to be continuous coordinates. But you need to keep in mind that it is actually discontinuous. So x minus x price has a bound that is the constant of the lattice. So which means that in the momentum space you need to what you integrate is to 0 to some cutoff. Okay, this is the key point. Anyway, what we do is this is what we do. Okay, COAR. Let's see. I check the pronunciation. Is it coarse?
Coarse.
It's a coarse. Coarse grained. Coarse grained. Yes, it's coarse grained average. That's great. Then here we have some program that is we don't know how to write the free energy functional in terms of the field rather than the spin. Maybe you want to derive the explicit expression by the first principle from the original form of the partition function, but there's no need to do so, because what we do is in some it is just like something just you guess it, then you fit it. It is just something like fitting. Okay, so you just guess the shape, the expression of the free energy. But the only requirement is that the free energy should satisfy the same symmetry. Should omit to the same symmetries of the original system. For the original system, it has SOD symmetry and Z2 symmetry. So we should not write something like 5 to 3 is turned in the expression. Okay, so we just write it like this. This is the interaction, and this thing you can regard it as the free field theory. But when we need to figure out the expression of the three parameters. I need to check it if I have made some mistake in the parameter. Yes, parameter. We need to fix the parameters because they are unknown. You can determine it by fitting the exponential or numerical data, but here it's quite easy to figure that the curve K, okay, curve K is just 1, okay. The RU is remained unknown. Anyway, you can just fit it with the numerical result. Okay, that's great. Then we need to keep in mind there is a cutoff in the momentum space. Okay, then it's quite easy and it's quite happy to do the field theory by Feynman diagram. In a Feynman diagram, you can calculate the free propagator. It's just the inverse of this quadric. It's quadric operator. Yes. And let me check it. Quadratic. Yes, it's a quadratic operator. It's inverse. It's quite easy to calculate the inverse in the momentum space. This one just gives the k square, and this one is r. Okay, so this is a propagator. Then this thing gives the vertex. If you want to study the theory by perturbation theory, then it's quite easy to calculate the exact propagator with 1 pi expansion. This is a self-energy. And for self-energy, you can to the one loop order, you can calculate this formula. Okay, that's great. Here you need to keep in mind there is a cutoff. Okay, that's great. Then what we can say, what we want to know is a 2-point correlation. Sorry, the 2-point correlation. It has some physical meaning. That means what?
Susceptibility.
Susceptibility. Let me see.
Susceptibility.
Yes, it is susceptibility. This one. It is derived from the 2-point correlation function, say alpha beta. Yes. It is just how to say a response function. This is external field. Then this is response function. So actually, it is just the 2-point function. It's quite easy to calculate it by the Feynman diagram. That's great. Then you notice that the self-energy doesn't depend on the input and output momentum. This is because that you notice that this here k input, then out is k. So in the loop there is no other dependence on no dependence on k. So it is a function. It is not a function of k. Okay. Then we can the how to say the susceptibility we measure in lab is k0. We take k to 0. Then you do the integral, and you found that there's two distinct yes, there is two distinct behavior of chi. Okay, for d is larger than 4, you see that 1 over chi is this formula. Okay, here we notice that what is the mean of S. S means R minus R critical. The critical is that the critical value of the phase transition. We need to record that we need to record the pressure of phase transition. The phase transition happened in the place where R trans is sign. Because now we just discuss the spontaneous breaking that we just for the roughest approximation, we just take the field to be a constant in this range, because this you would take as a function, this then will give a positive contribution to the free energy. So it's better to take the field to be a constant. When you take it to be a constant field, then you just need to take it to consider this 2 term. Now this 2 term, and you must be positive, because we need the free energy to be bounded below. Okay. Now this thing, when R is positive, then the plot from F for F is like this one, and when R to be negative, you see that there is a spontaneous breaking and spontaneous symmetry breaking, then there is a phase transition. For the critical value is R to RC to 0. Okay. But we want to study the behavior near the critical point. So we take R to be quite small. So the distance between the state to the critical point is described by R minus RC. Okay, RC equal to 0. You see S here. Okay, that's great. Then you see that for the small perturbation, we can see that U is quite small, and then if U equal to 0, okay, it is just the result of the free energy. The free theory. But and then U is quite small. Okay, you see that the perturbation is quite small. That's great. But for D is smaller than 4, you see that. Okay, no, nothing. Okay, that's great. The U doesn't give the U doesn't give anything unusual. How to say? The bad thing is come from S. When S is quite small. When S is quite small, that means when your system is quite linear to the critical point. When you approach your system to the critical point. The critical point that you think you imagine that RC equal to 0 is a critical point, then you found that, then you do it, then do the expansion around the critical point. You see that? You see what? You see that when your system approaches the critical point, then the arbitrary small perturbation can have a divergent effect on your physical observables. Such thing cannot be correct. Okay, cannot be correct. So which means that the perturbation expression in U is not correct. We need to resummation it, which means just like this one. Okay, we need to resum. We need to do the summation from 0 to infinity. Or if you give a cutoff, oh my God, you just you have you have a divergence. Okay, that's great. Now how to understand it? We need to notice that there is a new symmetry of the critical point at KC. This is not represented in the underlying Hamiltonian. Maybe you can just understand this symmetry as a consequence of the divergence of the correlation length. The correlation length is calculated by the 2-point by the 2-point correlation function. Okay, that's great. The C divergent, the C become divergent, which means that there is no correlation between 2 points. So we have a scaling symmetry. Maybe I think is right. So the characteristic length scale equal to infinity. So the physics become invariant under scaling transformation. So the new coordinates is the old coordinates divided by as the scaling factor. Okay, good. Okay, so what we need to keep in mind that is physics in environment. Okay, that's great. We just study the free field. The free field survey we just look at here, and we require that the physics remain their form in the scaling transformation. Then we got the transformation of the field. Okay, that's great. It's quite easy. Just get it. Let me see. Okay, you got this one by this term. Then you got the relation of R and R prime. Okay, that's great. Then you know that for the 2-point correlation, you have this relation. Okay, that's great. Okay, so we just write it as with another symbol like this. This means that it's new coordinates, and the new R. It is the original model. Okay, good. Then you find some crazy thing. For initial value I larger than 0, you find this one. As L increase, then you found that I could go to infinity. This is the phase. This is represents the physics of the paramagnetic phase. This is because R go to infinity, when I go to infinity, let me see. This one just is it looks like this one. Okay, so n 0 is 0. Okay, and for r elective, you go to r to infinity. This is it represent the ferromagnetic phase. Between the divergent flows, we have a fixed point. This is a critical point. Okay, this is represents the phase transition between the two phases. Notice that at an RG fixed point, so we can see it R equal to R star. Okay, on both sides, which means that this is R star and this is R star. Okay, that's great. Then we just drop R star from the definition. Okay, so we just got this equation. Then it is quite easy to go to the power law from this relation. Okay, great. So you see that as a correlation function, 2-point correlation function, have a power law in at the critical point. That's great. Okay. Then our main result is that identify the Gaussian fixed point of the RG transformation. So then we look at the stability of the fixed point to add the perturbation to the action. So at first, simply is that we need to we can introduce a aquatic coupling U. Then we have RG flow. Okay. This is okay. The Gaussian fixed point is still R star equal to 0 and U star equal to 0. That's great. But there's some key point. That is for d larger than 4. Okay, d larger than 4. The flow of U will flow back towards U star as L increase. That's because this is minus. Okay, you know that U is positive, and any U by any U evolve by this differential equation will go back to U equal to 0. But for D is less than 4, this is positive, so it will evolve go out. Okay, this means that we have to flow from U star equal to 0, which means that this fixed point is not stable. Is not stable. When we have a new fixed point known as Wilson fixed point. Okay, this fixed point is Q. Will Q the program with perturbation theory in D less than 4. Okay, that's great. But how to see it? It's better to work in the momentum space. This is because in momentum, how to understand it? I got some puzzled. I need a puzzle about this. Anyway, when work in the momentum space, we need to know that the skinny transformation will make the cutoff go to another cutoff. Yes. Lambda go to another lambda. Okay, so new idea is that how to say it means what? It is the decimation.
Decimation.
Yes, the key point is the decimation of the degree of freedom. I think the idea is not is a little deeper independent with the conformal symmetry at the critical point. Okay, the conformal symmetry at the skin invariant at the critical point is some physical insights, not the mathematically conclusion. But the decimation of degree of freedom is just some mathematical method. Okay, it's just approximation in mathematics. So you can understand it easily. Okay, that's great. We just to divide the field to two parts. One part is for the low energy and one part is for the high energy. Okay, that's great. Then you can just when you calculate the path integral, you just to integrate the high momentum field. Then you got an effective theory for the low energy physics. This is the key point. Then we need to and we try to do it. Okay. And finally, you need to drop other correlation, because this correlation will this coefficient will will be surprised during the RG process. Okay, this is what we want to see. Then you can see what is the new physics. The new physics with cutoff lambda over b has new parameter. The new parameter is related to the old ones by this formula. Okay, then you do something. Then you do the rescaling step. The rescaling step will make you require the rescaling step to make the theory invariant. Let me see. Okay, that's great. Why we need to do the rescaling step? It's just a transformation. It is just a transformation, I think. Yes, it's just a transformation. Then you get this one. Then you do this one just to put the energy cut off to lambda again. Then you can do this again and again. Okay, that's great. So it will become an RG flow equation. The RG flow equation will collect the information for the high energy physics to the low energy physics. So anyway, I think it's one. Then you can try to solve the fixed point of the equation by set the left hand side to be 0. Then you found or you can just drop the diagram, and you found there is another fixed point here. What is then? What can we tell us? We need to notice that in the original model we just have one parameter, that is k. Okay, so in principle, the two parameter I and U in the lambda theory free energy functional should depends on k. Okay, so the real system should lie on a line, a curved line with dashed line. Okay, that's the style. Then for k is quite small. It located in this region. For k is large, and it locates if it is located in this region. Then you see that in the RG flow, this region will map to the minus infinity, and this region will go to positive infinity. So the two regions have two different phases. Yes, and the point A will be mapped to this fixed point. It is a critical point. The fixed transition happen on A. Okay. Then you notice that this fixed point is maybe it's not so stable because this point this point will go to infinity. So actually it's not a stable point. But let me see. But it's not so important. Maybe we can imagine that the real system like this one. This one. What? You see that it will also go to the WF fixed point. And the most important thing, the most important thing is that the Gaussian fixed point is quite quite unstable, and this one is quasi stable. So this fixed point is actually the phase transition. The phase transition actually happen on this point, not this point. This is the key deep. This is the case for D larger and D is more than 4. Okay, that's great. Let's end it. That way, maybe we can continue to discuss some advanced topic. Initial function. Then what can we get if we know that the theory has another fixed point? What can we get? We can study the behavioral system near the fixed point, which means that we can derive the exponent for the phase transition. This is what we want to get. Okay. But we can also need to accompany the treatment of the fact need that we need to define the algebraic scaling of phi by a anomalous dimension. It is a little different between the formal discussion. That is B d minus 2 plus eta over 2. Why we require it? Why the anomalous dimension appear? And you can calculate it. But you cannot use a Feynman diagram because the Feynman diagram is not right, I think. Yes. How to get the eta? Let me see, sorry. I'll see how to get the eta. I have some question to understand it. Why we need to introduce another parameter and how to calculate it. First, the formal analysis can just tell us, oh, okay, there is another fixed point, and what can we get? What can I get? Yes, we can just to write down the approximation of the differential equation. We can use the linearized one equation. Then we can solve the linearized equation to obtain the exponent of this transition. This is what we get. Okay, the phase transition should be written as a power of the distance. The distance between the state to the critical point is labeled by Kc minus k. Okay, that's great. Okay, good. But why we need to do the field renormalization? The entire element size did not modify the original scaling of the field. Yes. AC is actually an artifact of walking to the first order in epsilon. At high orders in epsilon, we do find a momentum in the self-energy. Yes. For one loop case, you notice that in the formal element size, we just use the one loop summation for the self-energy. But in high orders, we need to consider two loop correction. So this will give a renormalization of the gradient term. So we need to choose the RG scaling for phi. Oh, that's great. That's great. We need to recall that when we calculate the self-energy. The self-energy, why it have a epsilon? Why it will have a epsilon for the two loop correction? This is the key point. This is the key point. Two loop. Okay, I just found it. This is self-energy. Let me see what is the self-energy. There's no d minus 2, d minus 4, something like this. I just want to why we got the factor d minus 4. Or maybe it is just come from the integral. You notice that yes, when you need to run a calculator, then you can find it. Why the epsilon approx? Yes, self-energy. So we need to so the normalization of the field will be changed by the enormous dimension. Enormous. Well, US.
Anomalous.
Yes, anomalous dimension. Okay, great. Then how can we calculate it? Yes, I think no, we cannot got it. At the first order, sigma eta is k independent. However, in the second U, okay, the second of U, we have a momentum independent sigma because the k input and the k. Okay, is some the k will input in the definition of the sigma. Okay, and sigma becomes this one. To need innovation order in epsilon, you can see it this one. And you can calculate it. Then you can go to the eta. Why we can go to the eta? That is because eta will appear in the two correlation function, so you can calculate from the self-energy. So it means that the perturbation theory still work. So why here? Let me see. But actually, we have seen that there is a divergence. There is a long physical result in our perturbation calculator. of this one. Why this one is wrong? Okay, that's because the key point is that the Feynman diagram is right. Okay, it's right, but your understanding of the fixed point of the phase transition is wrong, because in the S expression you see, you just think, just in your mind you just think, okay, that RC equal to 0, U equal to 0, the Gaussian fixed point is stable. You think that no, it's not stable. Okay, this is the Feynman diagram calculated right, but your physics the physics in your mind is wrong. So you just what we do is just to regard the fixed point as another point, another fixed point. So everything will become good. Okay, this is a key point. Maybe we need to see from when S. You need to notice that S appear. Sorry, R appear in the definition of the propagator. When you do expansion among the Gaussian fixed point, then the 1 over k squared, the integral will definitely become divergent, but become divergent for divergent from for the delta r, but it will keep in, it will be finite for RC not 0. Okay, I think this is a key point. Yes, when you do the perturbation theory. It's great. I think it is a key point. Okay, you can just calculate the abnormous dimension. Then everything is right. Then you can calculate the correlation functions. Okay, good. Then you obtain as exponents of the phase transition. Okay, good. That's all.